Welcome back, and now we have the basic recipe at device level ready. We have gone to the DC characteristics of the MOSFET. From there we have understood how to arrive at the small signal parameters of the MOSFET at lower frequency. Then we have looked into the parasitic capacitances, their physical origin, how do they affect the signal propagation through the device, and finally we have added the noise sources to the device, looking at their physical origin and also incorporating them in the small signal model. Now we are ready for analyzing circuits using the model that we have developed. So let us start with our discussion on a simple circuit, maybe a common source amplifier with a resistive load, and try to carry out these basic operations. Remember, to start with, we discussed 4 basic operations. First is the DC analysis, so first is the DC analysis, second is small signal, we also need to take care of linearity or swing, signal swing or linearity. We will discuss this, what is the significance of swing and what do we mean by linearity. Linearity in itself is a more involved concept. Here we will go for a slightly cruder definition, which is signal swing. And finally frequency response, and at the end noise analysis. So using the concept we have developed so far at device level, we are in a good position to be able to do all this analysis, carry out all this analysis for a given circuit. So let us start with a simple circuit which is a common source amplifier with resistive load, and carry out all this analysis. So first we will be looking at the DC characteristics. You are applying a gate voltage Vg, you have some Rd, and you are looking at the Vd. So if we try to plot Vd versus Vg, so what kind of curve do we expect? We know that as long as Vg is lower than Vt of the MOSFET, there is hardly any current, the current is negligible, Id is 0, therefore the Vd is going to be just equal to Vdd. So, start with Vdd, it will remain clamped to Vdd till we reach Vg equal to Vt. Beyond that point, if I go on increasing the gate voltage further, our current is going to increase and the Vd can be written as Vdd minus Id Rd. So, this is cutoff region, right, because MOSFET is cut off, Vg is lower than Vt, there is hardly any current. Beyond this point, if I see the drain voltage is starting to fall as the current is increasing and Vg is increasing beyond Vt, but still Vd is much larger than Vg minus Vt, right. So, for saturation region operation, the condition is the Vd should be greater than Vg minus Vt. It is just started to fall down and it will go on falling, and this entire region will have saturation region operation of the MOSFET. So, we will have a steep curve as you are increasing the Vg, the Id is increasing as per square law, and you are going to get a steep increase reduction in the drain voltage. So, you get a steep reduction. Beyond a certain point, when you reach say Vg naught, at this point, suppose the drain voltage after falling so much, the condition has reached where Vd at Vg naught is equal to Vg naught minus Vt. So, beyond that, if you increase Vg further, definitely Vd is going to drop below Vg minus Vt and it is going to enter into triode region, and in the triode region your equation is going to be governed by Vgs minus Vt into VDS. If I ignore the small VDS square, suppose VDS square by 2 is ignored because of it being small. So, this is the expression that we get in the triode region. Beyond that point, if you try to increase Vg further, you are trying to reduce VDS further, because if VGS increases, ID is supposed to increase, and that is supposed to reduce the VDS, and therefore, this is trying to increase, but this is reducing. As a result, these two factors will cancel out each other, and the current will saturate to a very small value finally, and you are having a triode region operation. The voltage over here will approach close to 0. So, here in this region we have saturation region operation with a large slope, and finally, at the point where Vd is equal to Vg naught minus Vt is reached, we are hitting the triode region, and beyond this point the MOSFET is in triode region. So, we know that if you are trying to operate this as a digital inverter, so the region of operation happens to be either the cutoff region or it happens to be the deep triode region where the input voltage is sufficiently high. So, definitely this is this probably the first integrated circuit inverter or digital inverter that people had used before the implementation or invention of CMOS technology, because at that time the only transistor available was NMOS, and this was one of the ways of implementing the inverter rather than MOSFET. Of course, those days it used to be BJT, but this was the first inverter, and this is the inverter characteristics. If you apply input voltage which is very close to 0, digital logic level low, output is close to VDD, and if your input is much higher than a certain value close to VDD, the output is close to 0. So, this is the inverting operation, and for inverting operation we use these two domains. Digital inverter, we use these two domains, but in order to have analog operation, we are supposed to get a sufficiently large signal gain from input to output. That means, if I am changing the gate voltage over here by small amount, that is I am putting a small AC signal in series with this gate, my drain voltage should also change by a large amount, and that will happen when the V out by V in slope, that is Vd versus Vg slope, is having a magnitude larger than 1, and we see that in this curve the central region of course is having maximum slope, and therefore, it is going to give me maximum possible gain. Therefore, I would like to bias my transistor in the saturation region. I will try to find out the operating point such that it is in saturation region. So, let us look at the biasing consideration. Capital Vg denotes the DC value, small Vg the small signal that you are applying on the top of this, and you have the Rd, once again capital Vd the DC and small Vd. Now, if we talk about the best possible biasing point, we need to look at certain consideration. One is definitely the gain, and we see that in the central region we are going to get possibly largest gain. Another important consideration happens to be signal swing that is available to us. So, if I look at the DC voltage at the gate, that is suppose capital Vg, we are fixing the DC bias point. In order to operate this circuit as an amplifier, the first thing once again is to fix the DC operating point or the DC bias. So, we fix the Vg. So, corresponding to that I also have the Vd fixed. The DC voltage at the gate and DC voltage at the drain are getting fixed, and on the top of that I am going to apply a small delta Vg plus minus, and corresponding to that I expect my Vd to change. So, if I am reducing my Vg, the current reduces and the Vd goes high. If I am increasing my Vg, current increases, Vd goes low, and the slope over here determines what is the change in delta Vd in both directions when I change my gate voltage by delta Vg. So, the slope is significantly greater than 1, that means we are going to get significant gain. Now, one of the requirements that we have for good amplification and signal swing is that the amplifier should be the transistor should be always in saturation region. The moment it goes out of saturation region, we are going to get poorer gain. We have seen that the moment you are at this point, the slope of this curve is almost dead, and therefore, if you are biasing your transistor over here, the gain is going to be very poor. Likewise, if you are biasing your transistor over here, the gain is going to be very poor. Now, if you are biasing your transistor over here, you have certain rooms on the positive side. You can increase your output signal to this point without significant distortion. Likewise, you can reduce your output signal to the corner point over here without significant distortion. So, this curve tells me what is the maximum room available for my signal on the positive side and on the negative side at the output terminal. So, as compared to the Vg, if I say my as compared to the DC gate voltage Vg, my input signal is going up by small Vg. Corresponding to this, this is the DC level Vg. Corresponding to this, my Vd is going to have the opposite excursion, but magnified. So, what is the maximum value that the Vd can take without getting distorted? That is of course, the VDD, because the maximum supply available to you in this circuit is VDD. So, it cannot go beyond VDD. So, in case your input signal is going so low that the MOSFET at a particular point hits the output voltage at a particular point hits VDD, then definitely at this point it will become clamped. So, if I magnify this region, what is happening? If I just look at this region where this clamping is taking place, so my input signal is going sufficiently low, it may hit Vt, right. So, input signal, suppose it goes so low that the overall voltage over here, capital Vg plus small Vg, is getting lower than Vt. In that case, definitely whatever point, suppose this was your Vg and your input signal hits Vt over here. So, this is your Vg, or you can say the instantaneous Vg, I can call it Vg dash, which is hitting Vt at this point. So, at this point my current is almost 0, and therefore, the output voltage over here corresponding to this point, it will hit VDD, and for the rest of the signal which is below this, it will remain VDD, right. So, you are getting the signal clipped at VDD. Therefore, the maximum output signal that I have, it is VDD. So, maximum output signal Vd max I can have is VDD. What about Vd min? For Vd min, what is going to happen if I go on increasing the positive peak of the signal? If I go on increasing the positive peak of the signal, we can see this curve what is going to happen. If I increase the delta Vg further and go on to the positive side, ultimately the output voltage is going to be too low and it is going to be in triode region. Once again, the gain is going to be hampered, and therefore, in order to make sure that the transistor is in saturation, even for the worst case when the gate voltage has sufficiently increased, I must make sure that the drain voltage is sufficiently or minimum value of the drain voltage is equal to the voltage required to keep the transistor in saturation. So, if I ignore this small signal at the gate with respect to this DC gate voltage, what we have seen is the minimum drain voltage allowed to keep this transistor in saturation is going to be Vg minus Vt. The moment drain voltage goes below this Vg minus Vt, we are pushing the transistor in triode region. So, what we can say is Vd min is going to be Vg minus Vt. Therefore, we have this range from VDD to Vg minus Vt. My signal can go maximum up to VDD, it can go minimum up to Vg minus Vt. So, if I want a sinusoid signal at the output, so that it can have symmetric swing on both sides, means the peak to peak signal is symmetric across a DC point, I want equal room for the signal on positive side as well as negative side with respect to the DC bias point. So, what is the point we will choose? So, that will be the midpoint between these two extremes. So, Vd I would say bias should be equal to Vd max plus Vd min by 2, which in this case is Vdd plus Vg minus Vt by 2. And based on this, I can decide what is going to be the Rd value, because this Vd bias is nothing else but Vdd minus Id times Rd. So, this DC bias current Id and Rd determine what is my Vd. So, from this equation I can find out what is the Rd value required to get a DC bias point at the drain, which is allowing maximum symmetric swing on both sides as compared to the DC point. So, if I choose Rd according to this equation, my output signal can go up and down by the same magnitude without pushing the transistor into triode region or the cutoff region. That is a crude definition of signal swing. Why crude? Because this is just ensuring to the first order that the transistor is going to remain in saturation region. It is not going to enter cutoff, it is not going to enter triode. But definitely there are more serious considerations related to linearity and distortion that we may cover towards the end. For the time being, we are skipping that discussion in favor of the time. So, remember that for a good amplification, what do we really want is that this slope should be perfectly linear, should be constant, but no way you can get this slope constant in a practical device. If you plot the slope, it will be kind of peaking in the center. If I just take a reading from a device in a lab and try to get these characteristics and plot the slope, it is something like this. So, the slope peaks at the somewhere in the middle and then again dies down. So, the gain or the slope is not constant, and a result of which the gain itself, the slope which determines the gain itself, is dependent upon the Vg, or it is dependent upon the signal swing. So, if your signal swing is only till this point, the gain experience will be different. The signal is going till little further, that part of the signal will experience different gain. So, different part of the signal will experience different gain, and that leads to non-linearity. It is not a constant function. Ideally, I would like my V out to be equal to k times V in. Ideally, k should be constant independent of V in, but here k will not be independent of V in. If the V in is larger, magnitude is slightly increasing the small signal magnitude, the slope, since the slope itself is dependent upon the absolute input value, this will start depending upon V in, and this is no longer be constant. Therefore, V out is no longer linear function of V in. There we get all kinds of harmonics coming into picture. So, we can more accurately represent it as some, if I just look at the small signal, it will be A1 times V in plus A2 times V in square plus A3 times V in cube, and so on. So, if you look at this curve, you can find out the fitting function which is satisfying this equation, and from there you can find out the values of A1, A2, A3, which is depicting the overall transfer function. So, this is the real picture that we get. We want only the first term, but we are getting all kinds of other higher order terms which are not desirable, which are distortions, and this lead to harmonic distortion. So, if you are inputting a sinusoid of sin omega t, and if you are having the second term A2 times V in square, it is going to lead to sin 2 omega t term. This is going to lead to sin 3 omega t terms, and therefore, you are having harmonic distortions. You are having harmonics of the input signal present at the output, which is undesirable. So, this concept of harmonic distortion becomes very important when we are talking about high resolution signal processing. So, definitely we will come back to this concept of non-linearity and harmonic distortion when we approach our discussion on the front end amplifier and ADC. For the time being, whatever analysis we do, that will be based on this relatively cruder definition of maximum signal swing at the output, where the only justification that we need is keeping the transistor in saturation region, making sure that the transistor is not going off or it is not entering into triode region for lower and higher excursion of the input signal. So, that is the point we are going to analyze for the time being. The DC biasing of the common source amplifier. So, what we have seen is that we are going to require an appropriate choice of Vg and Vd. For a given Vg, we are going to get a DC operating point, and we wanted to set this Vd to the midpoint of the extreme allowed voltage of Vd min and Vd max, and that is how we determine the Rd. That is the first step in the circuit analysis. We are trying to find out the DC operating point of the circuits by appropriate analysis. Now, let us go further and try to look at the small signal model of this circuit and figure out the small signal analysis. So, for this circuit is I would say this is the simplest possible circuit in analog electronics, and we are just going through some essential steps which is going to be repeated for more complicated circuits like differential amplifier, two stage amplifiers, and finally the complete analog front end. So, this is just an example case. We also need to discuss in detail the common source amplifier with active load, that is another important concept that is going to be used in building the front end amplifier that we are looking into. So, once we have appropriately set the value of Vg and the Vd, so that my transistor is biased in the high gain region. So, I have a certain correct choice of Vg, corresponding to that I am having a correct choice of Vd, so that I am my DC point is at a point in this curve where the slope is large and little bit of change in Vg is going to give me a large change in Vd and therefore large gain. Now, on the top of this, if I want to do the small signal analysis, I can look at the MOSFET model first. The first step happens to be drawing the MOSFET model. Here remember that we are ignoring the body terminal. So, I am not drawing the body terminal, assuming that the body terminal is grounded. Somebody pointed out that we should have included the GMB term, but just to keep things simple, we are ignoring that effect for the time being. So, assuming that the body terminal is grounded, we will be looking at how to include the parasitics also. So, this is the the model of the MOSFET that we have at hand, 3 terminals, gate, source and drain, and now we have to look at the connectivity between these terminals and AC ground. So, first thing is what is appearing at the gate. So, at the gate, as we said, we have some DC bias which is capital Vg. On the top of that we have a small Vg, and in order to look at the small signal we can set this capital Vg to 0, because this is a DC, is not having any small signal. I can directly put a small Vg over here, and that appears between the gate and the AC ground. Likewise, at the source we directly have the AC ground. In this case, gate is grounded, source is grounded. RO appears always between the drain and the source. So, common mistake in papers that we correct often is that people draw RO between the drain and the ground, even if the source is not grounded. So, it should always be taken care that the RO appears between drain and source and not between drain and ground. And then finally, we have RD between the drain and the VDD, which is again between the drain and the AC ground, RD. And therefore, in this case it is simple to solve. We do not even need to solve any KCL, KVL. We can see that whatever Vg is appearing over here, that is effectively Vgs, because source is grounded. Therefore, Gm Vgs is going to flow into the output node, and that is going to flow in this parallel combination of RO and RD. Therefore, the voltage over here is just going to be Gm Vgs, that is the current, multiplied by RO RD. So, this is 0 0 minus RO parallel RD times Gm Vgs. So, V out in this case is nothing else but minus Gm Vgs times RO parallel RD, because this is a parallel combination, RO RD appearing between drain and the common AC ground, and the voltage here is the total current flowing through RO and RD parallel combination times that resistance, and therefore, V out by V in is just minus Gm RO parallel RD. And if RO is much greater than RD, which is generally the case in the designs, RD that we are choosing may be significantly lower than RO in general, we can just approximate this as minus Gm RD. So, in this circuit, if I say what are the mechanisms that are available for us to increase the gain, either we can increase the Gm or we can increase the RD. So, if we increase the Gm, again what are the options available to us? Either we can increase the W by L or I can increase the RID. So, once again, when I am for a given RD, if I increase ID, what we are going to have is the drain voltage, the DC voltage at the drain is going to go down, and therefore we are going to have limited swing available. So, we said that Vd needs to be midway between the Vdd and Vg minus Vt, so that you have symmetric swing available on both sides. So, if you are increasing the Id, the drain DC voltage goes down, it can come over here and it can reduce the swing available in the lower direction. Same thing will happen if I try to increase Rd while keeping Id constant. So, let us keep Gm constant and increase Rd. So, once again, if you are increasing Rd, once again the DC drop across the Rd is increasing, as a result of which the room available will be reduced. If we want to say maintain the signal swing, one of the possibility is that I reduce the Id. So, suppose I reduce the Id, make it half. So, Id dash is Id by 2. That means my Gm dash is going to be Gm by root 2, because Gm is proportional to root Id. Now, corresponding to this, of course, I am seeing that my Gm has gone down. So, can it help me in achieving larger gain while maintaining the signal swing at the output? So, here if my Id is reduced to Id by 2, I can increase my Rd to twice while maintaining the same DC point at the output. So, I was at this point to begin with, I had a certain Id, I was at a certain Vg and Vd, and therefore, I had biased my amplifier at the midpoint, lower and higher side, we have equal room. But now, if I reduce the Id by 2, Id to Id by 2, then of course, I can increase the Rd by the same factor to go back to the same DC point Vd. And what does that mean effectively is, in this curve how will we obtain it, how do we rationalize this. So, if I look at the original curve, this was the original curve, I was at a midpoint of the two extremes and I had certain certain Vd and a certain Vg, this was my DC operating point. Now, what I am saying is I am going to reduce my current by half. So, basically that means that for this MOSFET, if I follow square law, that means I have to reduce my Vg by some amount. So, that Vgs minus Vt square is reduced to half, or the DC current is reduced to half. That means of course, I am shifting, I am going towards lower values of Vg, I have to reduce my Vg. So, in order to reduce the Vg, I can parallelly increase the value of Rd, because my requirement is that the DC point should be midway. So, if I increase my Rd, what happens to this curve? This curve basically becomes steeper, and therefore, for a larger Rd, once again at the desired Vg I will have my new DC operating point, and in general this slope will be almost similar to what we have over here. So, what we are trying to do is we are trying to play with the DC bias current and the resistance to increase the gain while maintaining the required signal swing. Remember, the target is that we should keep the DC bias point midway between the two extremes. So, we reduce the current to half and increase the resistor by double, so that the DC point at the output is same. As a result, what is happening? Gm is reduced to by root 2, but Rd has been reduced to Rd dash is now 2 times Rd. Therefore, this implies that the Gm Rd, if I call it Gm Rd whole dash, that is the new value of Gm Rd, that is going to be root 2 times initial value of Gm Rd. So, we can see that by appropriate choice of Rd and the bias current Id, we can definitely increase the output gain while maintaining the same signal swing without disturbing the maximum signal swing at the output. Definitely, we do have the dependency of many other circuit metrics on Gm and also Rd. So, intuitively speaking, we have seen that the MOSFET is having parasitic capacitances, and when you increase Rd in this branch, the time constant, for example, resulting from the parasitic capacitance between the drain and ground CdB, which is going to appear between drain and body. Body is grounded, therefore, CdB is appearing between drain and body. So, if I just look at this capacitance and Rd, we see that the RC time constant at this node is going to go up, and as a result the circuit is going to become slower if I go for larger Rd, that is going to slow down my circuit. So, although I have managed to increase my gain, but I am suffering with the bandwidth, my bandwidth will be going down because of this capacitive behavior of the MOSFET. Likewise, we have also seen that the GM can play an important role in determining the noise. So, if your GM of the input device is going down, although you are trying to maintain the similar gain, but once again the input referred noise can be deteriorated. So, once again we have a stringent trade off with other parameters. You are trying to adjust one of the parameters, trying to increase the gain while keeping the swing same, but other parameters like the bandwidth and the noise, they are going to degrade, linearity is going to degrade. So, we have to take care of the requirement in the design. While optimizing one parameter, we have to make sure that we are still meeting the other requirements. So, here while reducing the ID and increasing the RD, we are managing to get larger gain and keeping the swing same, but at the same time we are going to deteriorate the bandwidth, we are going to deteriorate the noise. So, in general this is a general taste in the analog design. You are trying to meet a certain spec, you have to make sure that all these different specs, gain, bandwidth, noise, linearity, swing, slew rate, all of these are getting met. If you try to tweak with one of them, something else will be getting messed up. So, this is a small example regarding the DC analysis of the common source amplifier. Thanks a lot.